For decades, controlling a factory meant mastering physical hardware. You operated heavy manual switches to drive relays and managed control boards covered in analog gauges. When something broke down, troubleshooting required a technician to physically trace individual wires through dense, room-sized cabinets to find a fault. As industry transitioned to digital programmable logic controllers, or PLCs, early software needed to be accessible to those same hardware technicians. The solution was ladder diagram, a language engineered specifically to mimic the visual layout of physical relay logic. Instead of splicing actual wires on a greasy factory floor, engineers could now sit in front of early graphical computer interfaces and drop virtual contacts and coils onto a screen, accelerating the design process. Industrial automation now involves high-speed data acquisition. To support predictive maintenance, machines process complex mathematical arrays, a task pushing visual relay diagrams past their intended design. This demand for data has forced standard operational technology to collide with IT. As a result, today's engineers face a crowded menu of programming options, blurring the line between a traditional electrician and a software developer. To see how your language choice impacts workflow, we look at a baseline mechanical task, turning on a single LED when two separate switches are pressed simultaneously. We will run this logic through the hardwired inputs and outputs of a standard PLC Next starter kit. To make that single LED turn on, a programmer must choose between three distinctly different approaches to write the code. First, you have the legacy options specified under the IEC 61131-3 standard. For this exercise, we'll look at the visual formats of ladder diagram and function block. Second, you have a modern outlier, C++, a text-based IT language now available to run inside PLC environments. This chart plots effort against complexity. Traditional hardware actions, like our dual-switch LED, sit in the bottom left. Advanced network processes sit top right. Focusing on that bottom left quadrant, all three languages yield the exact same physical result. Because the hardware output is identical, deciding which language to use isn't about capability. It comes down to matching the efficiency of the code to the programmer's background and the long-term data requirements of the machine. We can evaluate trade-offs directly using this matrix, comparing setup friction, primary users, and ideal tasks. Starting with ladder diagram. As a native standard, it offers low setup friction. You draw logic using virtual open contacts and coils that look exactly like electrical schematics. When you press both physical switches on the starter kit, the two visual contacts close on your screen, completing the circuit to energize the output coil and turn on the LED. This one-to-one mapping makes it highly readable for hardware-focused electricians. The trade-off is structural. If you try to build heavy data arrays or perform complex math, the screen quickly fills up with an unmanageable clutter of rigid visual rungs. That brings us to the second standard option, function block diagram. Notice that function block abandons the simulated electrical wiring of ladder entirely. Instead, it processes data through standardized Boolean logic gates. To solve our starter kit problem, we pull an AND block onto the screen. The two switch inputs feed into the left side, and if both are true, the LED output flows from the right. This method provides clean routing for logic-heavy calculations. But by removing the electrical symbols, you sacrifice the direct visual map to physical wiring that legacy maintenance teams rely on. Even with that difference, both of these IEC visual languages serve the same primary goal: rapid deployment and intuitive floor-level troubleshooting. They are designed to keep the machine running, not to extract complex data from it. Finally, we turn to C++. Because C++ is not a native IEC language, it requires a steep configuration phase. Code must be written in an external editor, like Eclipse IDE, and then imported back into the system. This creates significant manual overhead. You have to individually code and assign input and output ports in your project file just to teach the external logic how to talk to the physical starter kit. The visual blocks are completely gone. The logic itself is reduced to text-based symbols, utilizing a typed ampersand to bridge the two switch variables. You endure this configuration time for a distinct payoff. C++ enables specific high-level functions like logging predictive maintenance data, tasks that are cumbersome to run in a visual ladder diagram. But while C++ provides unparalleled flexibility for complex math, applying it to a basic LED switch is overkill. It requires hours of setup to perform seconds of logic, and leaves the average factory technician staring at a wall of text they cannot easily troubleshoot. Follow this decision tree, starting with your primary task. Does your system require continuous data extraction for analytics, or just hardware sequencing? For IT programmers integrating machine metrics into a dashboard, C++ offers the most familiar environment for complex data bridges. The extra configuration time and external software layers are a calculated investment to capture and transform Industry 4.0 data for high-level analysis. But if your machine strictly handles hardware sequences, follow the left path. The choice hinges on your maintenance team's background. For traditional electricians, select ladder diagram to keep troubleshooting intuitive and reduce downtime. If your team prefers abstract logic, use function block. Do not over-engineer a simple physical sequence with complex IT code, and do not attempt to force a legacy visual diagram to execute heavy data analytics. The most effective automation engineers are bilingual. They choose standard visual languages to reliably run the physical machine, and deploy high-level text code